Environmental Systems and Societies for the IB Diploma program. Pearson book, 3rd edition, Chapter 4, Water, Section 4.4, Water Pollution. Guiding questions. How does pollution affect the sustainability of environmental systems? How do different perspectives affect how pollution is managed? 4.4.1, Water Pollution. Water pollution has multiple sources, including sewage, agricultural runoff, industrial effluent, that means water waste from factories and mining, urban runoff, so water that hits the streets and runs into the storm drains, solid waste disposal, and oil spills. These can all have major impacts on marine and freshwater systems. Freshwater and marine pollution sources include runoff, sewage, industrial discharge. Okay, so we're getting the same list twice, apparently. Okay, industrial discharge, that's the same thing as industrial effluent. Discharge just means what's being expelled. Solid domestic waste. That's the solid waste disposal. Transport. So here they've listed transport. Interesting. I guess we'll find out some examples of what they mean by that. Waste from recreation and tourism. And energy waste. Sources of marine pollution also include rivers, pipelines, atmosphere, oil spills, deliberate and accidental discharges from ships, sewage from cruise ships, aquaculture farms, power stations, and industry. So lots of different sources of water pollution. Stormwater that washes off roads and roofs can have a more significant source of pollutants than sewage. So simply the fact that the water hits our cities, our buildings and whatnot, and then goes down into the drains and into the rivers, that can be even worse than dumping raw sewage directly into the water. Such water may contain high levels of heavy metals. It's like lead and cadmium, maybe arsenic, volatile solids, and organic chemicals. Studies of water quality during floods of the Silk Stream in London recorded that between 20 to 40% of stormwater sediments were organic and mostly biodegradable. Highway runoff has a concentration of heavy metals that is 5 to 6 times that of roof runoff. Okay, so water that hits highways collects a lot more heavy metals than water that hits a roof. Annual runoff from 1 kilometer of a single carriageway of the M1, a highway in the UK, included 1.5 tons of suspended sediment, 4 kilograms of lead, 126 kilograms of oil, and 18 grams of hazardous polynuclear aromatic hydrocarbons. Well, that's bad. Okay. So types of aquatic pollutant include floating debris, organic matter, inorganic plant nutrients such as nitrates and phosphates, toxic metals, synthetic compounds, suspended solids, solid things that are suspended in the water, right? Hot water, oil, radioactive pollution, pathogens, diseases, light, noise, and biological entities, like invasive species. Pathogens means like bacteria or things that can spread disease, cause disease and spread disease. All right. So here we have an example, water pollution in the Flint River in Flint, Michigan, USA. Let's look at this example. The Flint River flows through the center of the town of Flint in Michigan, USA. For over a century, the Flint River has been used as an unofficial waste disposal site. Okay, so it's not legally a place where you're supposed to dump your trash, but people were doing it. For refuse, that means trash, from local industries. And the local industries are like car factories, meat packaging firms, and paper mills. Okay, so all of these industries were dumping stuff into the river. The river also received waste from agricultural runoff, so water that hits farmland, and then runs into the streams. Raw sewage from the city's water treatment plant. Okay, so somehow the water treatment plant wasn't just putting clean water into the river, it was also dumping sewage, which sometimes can happen if you have too much rainfall. Sometimes the water treatment plants can get overloaded. Toxins from leaching landfills. So landfills is like a trash dump, and then when it rains on the trash, that water that kind of leaches out of the landfill that comes out of it can have like nasty toxins in it and then go down into the groundwater. And urban runoff. That's just the water hitting the streets and the roofs and then going down into the storm drains. There are also claims that it caught fire on 2 occasions. Okay, if a river catches fire, it probably has some nasty stuff inside it because water shouldn't be catching on fire. As the industries boomed, so did Flint. Home to car manufacturer General Motors, Flint's population reached about 200,000. However, in the 1980s, rising oil prices and the financial crisis led to massive decreases in the working population. Flint's population crashed to 100,000 inhabitants, and with about 45% of the population living in poverty. So about 1 in 6 homes were abandoned. In 2011, Flint was in a desperate state economically, with debts of over $25 million. City governors made the decision to stop piping treated water from Detroit and to use a cheaper alternative, namely water from the Flint River. Okay, so they were paying a lot of money to bring water from a different place, clean water, into Flint. But they decided that it cost too much money. The city didn't have the money to do it anymore, so they started taking water from the Flint River instead. The water from the Flint River was highly corrosive and contained lead that had leached out of aging pipes in thousands of homes. So pipes used to be lined with lead, or even just made out of lead. And as these pipes get old and deteriorate, that lead gets into the water that passes through it. The change of water supply occurred in 2014, and residents complained of foul-smelling, discolored, and poorly tasting water. This went on for 18 months. Later studies revealed that contaminated water was contributing to raised levels of lead in the blood of about 9,000 children. So the children were drinking this water, and the lead was getting into their bodies to such a point that if in blood test, the blood tests showed that they had lead in their blood. Samples from over 250 homes found that about 17% of the samples had levels over 15 parts per billion lead, which is the state action level, so considered kind of a dangerous level, and that over 40% were above 5 parts per billion, indicating a very serious problem. The highest level recorded by a Virginia Tech study, that's a university study, found 158 parts per billion, so that's horrible. That's a lot of lead to find in a child's blood. In early 2016, a number of citizens and groups sued the city and state officials in order to secure safe drinking water. Among their demands were the proper testing of the water and its treatment for lead, the replacement of all the city's lead pipes, and the provision of bottled water to vulnerable population, those unable to get to free water distribution sites. So they were trying to put up places where you could go and get water, but not everybody could make it there. That didn't work for everybody. In 2016, a federal judge ruled in favor of the Flint resident and pressure group, and door-to-door deliveries of bottled water were ordered for all those without properly installed and maintained tap filters. So anybody who couldn't afford the right type of filters to clean the water in their home, the city was required to buy them bottled water and deliver it to them. The following year, it was announced that the city would have to replace all of the city's lead pipes. However, progress has been slow, and many residents continue to use lead pipes. According to the EPA, the Environmental Protection Agency, there is no safe level of lead in water. Okay, so we can't drink water with lead in it, any amount. It's not safe. 4.4.2. Plastic pollution in oceans. Plastic debris is accumulating, it's building up, in marine environments. Management is needed to remove plastics from the supply chain. So, too many plastics involved in the creation and distribution of products and disposal of products at the end. And to clear up existing pollution. Oceanic plastic pollution threatens ocean health, the health of marine species, food safety and quality, human health, and coastal tourism, and can influence climate change. Okay, and here we have a picture of a dead albatross with plastic debris in its stomach. Okay, the animals eat the plastic. They don't know that it's plastic. That's not food. Over 14 million tons of plastic end up in the oceans every year. The main sources are land-based, coming from urban and stormwater runoff, sewer overflows, right? So when the sewers get too much water in them, poor waste disposal and management, tire abrasion, that's like plastic tires wearing down, construction, industrial activities, and illegal dumping of plastic waste. So just people dumping it, right? Due to solar radiation and wind currents, plastic breaks down into small particles, called microplastics, which is under 5 nanometers, and nanoplastics, which is size under 100 nanometers. Being so small, these particles are easily ingested by marine organisms. So for a long time, people, a lot of scientists said that plastic was safe, that it was inert, that it wasn't like these other chemicals like lead, that it didn't get into the body and cause problems. Well, they were wrong. The most visible impact is the death of organisms caused by the ingestion, that means swallowing, of plastics. Microplastics have been found in tap water, salt, and beer, and have been found in tap water, salt, and beer, and are present in all the world's oceans. Several chemicals used in the production of plastics are carcinogenic, it means cancer-causing. The burning of plastic waste releases CO2 and methane, and so contributes to global warming. Plastic waste may reduce the aesthetic value, that means how nice something looks, of tourist destinations, and so lead to decreased tourist revenue. If there's lots of plastic trash everywhere on the beach, well, who's going to come visit your beach? It's gross, right? In addition, it may be costly to clean up polluted areas. Efforts are needed to reduce the amount of plastic that is in use and to promote circular economies, which means recycle, reuse, reduce. But circular economies, it also means like you reuse, like using the waste of something in another process, so that you don't have an economy which is based on extraction, using, and then dumping waste. Instead, having a more circular thing where you're extracting, you're using, and then you're like either reusing or recycling the waste into something else. So you have a circle going. One of the more successful campaigns has been the introduction of fees being charged in supermarkets for the use of plastic bags, making it cost money to have a plastic grocery bag. This has led to a major decrease in their use in some countries. In Ireland, for example, plastic pollution accounted for 5% of the pollution in 2001, but just 0.13% of the pollution in 2015, following the introduction of a levy on plastic bags. That means a fee. All right. Now we're going to look at an example, the Great Pacific Garbage Patch. The Great Pacific Garbage Patch is an area of marine debris, so trash in the ocean, approximately 135 degrees to 155 degrees west and 35 to 42 degrees north. It shifts its exact position every year, but remains within the North Pacific Gyre, a system of circular ocean currents, because it is confined by the ocean currents. So plastic and other types of debris come in, and then they get caught in this circular current and don't leave. In 2006, the UN Environment Program reckoned that every square kilometer of sea held nearly 18,000 pieces of floating plastic. Much of it was and still is in the Central Pacific, where scientists believe as much as 100 million tons of plastic waste are suspended in two separate gyres, large rotating ocean currents, of garbage in the Great Pacific Garbage Patch. Estimates of its size vary from 700,000 square kilometers to more than 15 million square kilometers, between 0.41% and 8.1% of the size of the Pacific Ocean. Plastics never biodegrade, so they do not break down into natural substances. Instead, they go through a photodegradation process, which is like solar radiation or light, breaks down the plastic into smaller and smaller particles that are still plastic. So plastic doesn't break down into its like organic components, which then can be used in different processes, but it just becomes smaller and smaller plastic. Problems caused by plastic. Plastic fouls beaches throughout the world. It makes them not look nice, makes them gross, and reduces potential income from tourism and recreation. So that's problem number one. Plastic entangles marine animals, strangles, makes them immobile, and drowns them. Okay, so this is the turtles getting caught in the soda can rings, the plastic rings. Plastic garbage, when washed ashore, destroys habitats. Plastic gets inside ship propellers and keels, making ship maintenance more expensive. Microplastics can accumulate in the food chain. Okay, so you build up microplastics in your body, and then something eats you, and then a bunch of others, it eats other animals that have microplastics, and then that one accumulates more and more microplastics in it. Plastic does not degrade. Plastic makes an ideal medium for the transfer of invasive species. So some species can, like little snails or whatever, they can latch on to these plastics that then float and carry them a long distance away from where they ought to be. And so on account of its sheer size and the small nature of some of its content, it is nearly impossible to clean up the Great Pacific Garbage Patch. Plastic garbage can be collected when washed up on beaches, but there are relatively few beaches in the region of the Great Pacific Garbage Patch. Some scientists have suggested putting booms, like big floating logs, around the patch and hauling in the plastic. However, the size of the patch makes this an impractical option. Others have suggested hoovering up the plastic, like vacuuming it up. Again, the sheer scale of this makes its success unlikely. Ultimately, it will be far easier to control the pollution at the source by reducing waste and increasing recycling and reuse. 4.4.3 Monitoring water quality. Water quality in freshwater aquatic systems is assessed by monitoring dissolved oxygen, pH, temperature, turbidity, and concentrations of nitrates, phosphates, specific metals, and total suspended solids. Okay, so these are different metrics that are used, things that are tested when you test how clean is the water. Data can be used to inform management strategies for reducing pollution. Okay, for example, if you know that there's high nitrates and phosphates in the water, you can look for the sources of those nitrates and phosphates and put a stop to them. Standard water quality tests on drinking water, rivers, and other sites can be performed with portable equipment. You can just take a case of it with you when you go out that enables detection of nitrate and nitrate ions, free chlorine, chloride and fluoride ions, hardness, so calcium, and traces of heavy metals such as lead. Water quality tests on rivers include biochemical oxygen demand, which is BOD, turbidity, ammonia, and dissolved oxygen. Okay, and then there is a table over here, table 4.14, chemical indicators of water quality, and it goes through this list of indicators So indicators is a metric that you're measuring, something that you're measuring that says something about the quality of the water. Okay? And then it shows you, like for example, a dissolved oxygen, so how much oxygen is in the water. And then it shows you the method, like how is that measured? In the example of dissolved oxygen, you have there's a test kit that includes a meter or a sensor, so there's some sort of little electric device that can test the oxygen content. Oxygen is usually measured as percentage saturation, so the percent of the water that is saturated with oxygen. Follow instructions to measure oxygen saturation. Okay, so there's usually instructions therein with the device. And then what the results show. Okay, so what does this indicator mean? So, okay, you get a result. You know how much, you get 75% oxygen saturation. Well, what does that mean? That means it's healthy, clean water. Anything above 75% it's fine. 10 to 50% oxygen saturation is usually an indication that it's polluted. Okay, and if you have less than 10% oxygen saturation, you probably have raw sewage. Okay, so that means it's coming directly from the toilets. And then you can go through this table on your own and look at what these different indicators mean. I think we're also going to go through these different factors like turbidity and temperature so you have a better understanding of what those are. So we've just introduced them, and now we're going to go through them. Direct measures take samples of the water and measure the concentration of different chemicals that it contains. If the chemicals are dangerous or the concentrations are too high, the water is considered polluted. Measurements like this are known as chemical indicators of water quality. Okay, so that's that table. Those are chemical indicators. But there are other methods as well. Indirect methods involve examining the fish and insects and other invertebrates, little creepy crawlies, that live in the water. If many different types of creatures can live in a river, the water quality is likely to be very good. So if you have high species diversity, you probably have pretty good water. If the river supports no fish life at all, the quality is obviously much poorer. Measurements like this are called biological indicators of water quality. So you have chemical indicators like dissolved oxygen, pH, phosphates and nitrates, salt, ammonia, and then you have biological indicators, which are related to specific species, both species diversity and then whether or not specific species are present. Turbidity. Turbidity is a measure of the amount of suspended sediment present in a water sample. Okay, so the amount of dirt floating in the water. A large amount of suspended sediment will give the water a turbid or dirty appearance, and this may indicate large amounts of organic pollutants in the water. To assess turbidity, use either a Secchi disc or a turbidity tube. The Secchi disc is lowered into the water, and the depth at which the markings can no longer be seen is recorded. So you have it on these strings, and then it's a black and white disc, you lower it into the water, and you watch it, and then when you can no longer see it, you take note of where on the string that is, and you pull it up, and then there's a measurement on the string. Okay, and that's how deep it was until you couldn't see it anymore. Temperature. Temperature partly limits stream oxygen levels. The lower the temperature, the more oxygen that can be dissolved in the stream. Temperature can easily be measured using a waterproof thermometer. Chemical tests. Dissolved oxygen. Bacteria use oxygen to break down organic pollutants. Therefore, streams with low oxygen concentrations may be experiencing pollution, for example, from raw sewage. Low oxygen concentrations have an impact on societies. Fish are unable to survive in streams with low levels of oxygen, because fish need oxygen to breathe. So a potential food supply is affected. Okay, so if there's no fish, we don't have any fish to eat. Oxygen levels can be assessed with a meter and a probe, or through the use of specialized chemical testing kits. Okay. There's water quality testing kits that you can use for that. Nitrate and ammonia levels. Nitrates are essential for plant growth, but levels of 50 parts per million are the recognized limits for safe drinking water. Okay, so some nitrates you need to have in the water, but too much isn't healthy for humans. High levels of nitrates may originate from agricultural fertilizers or manure and are associated with eutrophication. Test strips are available for the assessment of nitrate levels and ammonia levels. Okay, so these are little paper with some chemical on them that change color or show a marking or something if you to indicate how much nitrate or ammonia is in your sample. pH. Changes in stream pH are quite complex and may not necessarily be related to a particular source. As the acidification of watercourses mean streams and rivers, flowing water. The acidification of watercourses can be investigated, although it normally occurs over a very long time period. To measure pH, a pH probe or pH meter or test strips can be used. Okay, so you can have a device or these little papers that change color. 4.4.4 Biochemical oxygen demand. BOD is a measure of the amount of dissolved oxygen required to break down the organic material in a given volume of water through aerobic biological activity. Okay, so aerobic with oxygen, biological activity. BOD, biochemical oxygen demand. BOD is used to indirectly measure the amount of organic matter in a sample. BOD is usually measured as milligrams of oxygen per liter of water. Aerobic organisms means type of animal use oxygen in cellular respiration. Okay, so we are aerobic organisms. We use oxygen. The higher the number of organisms at a particular site, such as a river, and the faster their rate of respiration, the more oxygen they will use. So the BOD at any particular point in the river is determined by the number of aerobic organisms at that point and their rate of respiration. BOD can indicate whether a particular part of a river is polluted with organic matter, such as sewage or silage. This is because the presence of an organic pollutant stimulates an increase in the population of organisms that feed on and break down the pollutant. In doing so, they respire, they breathe, and they use up a lot of oxygen. This could eventually lead to a lack of oxygen and subsequent anaerobic decomposition, which then leads to the formation of toxic gases, such as CH4, hydrogen sulfide, and ammonia. BOD is measured using the following method. Take a sample of water of measured volume, okay? So like 5 deciliters. If this is not a liter, a calculation will be needed to give the usual unit of milligrams of oxygen per decimeter. Is that right? It should be decimeter cubed per liter. This also milligrams per liter as 1 decimeter cubed. Yeah, it needs to be cubed, right, to be a volume measurement. And then you measure the oxygen level, You place the sample in a dark place at 20 degrees in an airtight container for 5 days. The lack of light prevents photosynthesis, which would otherwise release oxygen and give an artificially low BOD. That makes sense, because photosynthesis creates oxygen. After 5 days, remeasure the oxygen level. The BOD is the difference between the two measurements of the oxygen level. 4.4.5 Eutrophication. Eutrophication occurs when streams, lakes, estuaries, and coastal waters receive inputs of mineral nutrients, especially nitrates and phosphates, often causing excessive growth of phytoplankton. Remember, phytoplankton is microalgae. Algal blooms only occur if phytoplankton growth had previously been limited by lower concentrations of phosphate or nitrate. Okay, so if the phytoplankton populations were being kept in check by low amounts of phosphate and nitrate, and then suddenly there's a whole bunch in the water, the population is going to explode because suddenly they have access to all of these nutrients. Okay, we saw earlier about the factors affecting phytoplankton productivity, and access to nutrients is one of those factors. Humans cause eutrophication when releasing detergents. It's like laundry detergents, types of soaps, sewage, or agricultural fertilizers into water bodies. It can cause algal blooms, oxygen starvation, and eventually the decline of biodiversity in aquatic ecosystems. Okay. In eutrophication, increased amounts of nitrogen and or phosphorus are carried in streams, lakes, and groundwater, causing nutrient enrichment. This leads to an increase in algal blooms as plants respond to the increased nutrient availability. As the algae die back and decompose, further nutrients are released into the water. This is an example of positive feedback. However, the increase in algae and plankton shades the water below, cutting off the light supply for submerged plants. So the macrophytes aren't able to get the amount of light that they usually get. The prolific growth of algae and cyanobacteria, which was formerly known as blue-green algae, especially in autumn as a result of increased levels of nutrients in the water and higher temperatures, results in anoxia, which is oxygen starvation in the water. The increased plant biomass and decomposition lead to a buildup of dead organic matter and to changes in species composition. Okay, so even though plants produce oxygen, when they die, they start to decompose. And then you've got bacteria and other things. It's these decomposition processes use up all the oxygen. Some of these changes are the direct result of eutrophication. For example, the stimulation of algal growth in water bodies, while others are indirect. For example, changes in the diversity of fish species due to reduced oxygen concentration. Okay, so some fish that need a lot of oxygen can't survive there anymore. Eutrophication produces a dynamic system. As levels of nitrates and phosphorus in streams and groundwater change, there is corresponding change in species composition. Okay, so different animals can live there. And different animals and plants as well, right? Because the macrophytes are also affected. Anthropogenic eutrophication. Human activities worldwide have caused the nitrogen and phosphorus content of many rivers to double, and in some countries, local increases of up to 50 times have been recorded. Okay. So let's learn a little bit more about phosphorus. Phosphorus is a rare element in the Earth's crust. Unlike nitrogen, there is no reservoir of gaseous phosphorus compounds available in the atmosphere. In tropical systems, phosphorus is more likely to be a growth-limiting nutrient than nitrogen, whereas in temperate regions, nitrogen is the main limiting factor. Okay, so how much productivity can there be? How many phytoplankton or plants or whatever can grow depends on how much phosphorus is available or how much nitrate is available. If there's not enough, they don't grow. Domestic detergents, that's types of soap, are a major source of phosphates in sewage effluents. Remember, effluents is the release of sewage. Estimates of the relative contribution of domestic detergents to phosphorus buildup in Britain's watercourses vary between 20 and 60%. As phosphorus increases in a freshwater ecosystem, the number of plankton increases, and the number of freshwater plants decreases. Okay. Nitrogen. Nearly 80% of the atmosphere is nitrogen. In addition, air pollution has increased rates of nitrogen deposition. That means nitrogen coming out of the atmosphere, coming out of the air. The main anthropogenic source is a mix of nitrogen oxides, mainly nitrogen monoxide, released during the combustion of fossil fuels in vehicles and power plants. Despite its abundance, nitrogen is more likely to be the limiting nutrient in terrestrial ecosystems as opposed to aquatic ones, as soils can typically retain phosphorus while nitrogen is leached away. So nitrogen goes away with the water. Nutrients applied to farmland through fertilizers may spread to the wider environment by drainage water percolating through the soil, leaching soluble plant nutrients, washing of excreta applied to the land as fertilizer into watercourses. Okay, so sometimes manure, poop from animals or people, usually animals, is put onto the land as a fertilizer. Erosion of surface soils or the movement of soil particles into subsoil drainage systems. So nutrients applied to farmland through fertilizers may spread to the wider environment through those processes. In Europe and the USA, for example, Chesapeake Bay, large quantities of slurry from intensively reared and housed livestock are spread on the fields. This is the manure from the big pig farms, right? They take the manure from them there and then put it out on the fields. Animal excreta is very rich in both nitrogen and phosphorus, and therefore its application to land can contribute to problems from polluted runoff. 4.4.6 Impacts of eutrophication. Excessive growth of phytoplankton is typically followed by their death. High rates of decomposition, rapid consumption of dissolved oxygen, which causes hypoxia, it's low oxygen, and anoxia, lack of oxygen in the water, and the deaths of aquatic organisms that depend on dissolved oxygen. A number of changes may occur as a result of eutrophication. Turbidity, which is the murkiness, right, the dirtiness, increases and reduces the amount of light reaching submerged plants, or macrophytes, the ones that are under the water anyway. Rate of deposition of sediment increases because of increased vegetation cover. This reduces the speed of water flow and decreases the lifespan of lakes. Net primary productivity is usually higher compared with unpolluted water and may be seen by extensive algal or bacterial blooms. These big areas full of algae. Dissolved oxygen in water decreases as organisms decomposing the increased biomass respire and consume oxygen. Okay, so the organisms that are so the organisms that eat the biomass, eat the algae. Diversity of primary producers changes and finally decreases, and the dominant species change. Initially, the number of primary producers increases and may become more diverse. However, as eutrophication proceeds, as it goes along in its process, early algal blooms give way to cyanobacteria. Fish populations are adversely affected by reduced oxygen availability, and the fish community becomes dominated by surface-dwelling coarse fish, such as pike and perch, as happened in the Wabigoon River, Ontario, Canada. Other species migrate away from the area if they can. In freshwater aquatic systems, a major effect of eutrophication is the loss of the submerged macrophytes, the aquatic plants. Macrophytes are thought to disappear because they lose their energy supply as there is a reduction in sunlight penetrating the water. Sunlight is intercepted by the increased biomass of phytoplankton exploiting the high nutrient conditions. In principle, the submerged macrophytes could also benefit from increased nutrient availability, but they have no opportunity to do so because the free-floating microscopic organisms shade them, block the light. Then there's an example here about the eutrophication of Lake Erie. I'm not going to read this example, but I think that you should. So on page 426, you can see some good pictures and the example of what happened to Lake Erie. So you get a good example of eutrophication.